Hi students, in this video we can discuss about carry lookahead adder. So we need to understand first why we go for such a carry lookahead adder design. So in our previous video we have discussed about the design of parallel adder or ripple carry adder. In this, for each adder block, the two bits that are to be added are available instantly. Like A0, A1, A0, B, E0, A1, B1, A2, B2, A3, B3, etc. like AN, BN. These types of binary inputs are directly available to each and every full adder block. But each adder block want to wait for the carry input to arrive from its previous block. This is the problem. The binary input bits are directly available, instantly available, but each adder block want to wait for the carry output from the previous stage. That carry output from the previous stage form the carry input of current full adder. So in general, the ith block wait for the I-1th block to produce its carry. The I-1th block's carry output form the carry input of ith block. So there will be a considerable time delay. This is the problem associating with this parallel adder circuit. There will be a considerable time delay due to the propagation of carry value. That time delay is called carry propagation delay. So due to this carry propagation delay, in a parallel adder circuit, it takes some time for generating the complete result. Okay, this is the case or this is the cause of the delay, that is the carry propagation delay. For example, consider a 4-bit parallel adder as shown here, and if each full adder stage has a propagation delay of 20 nanoseconds, means the full adder requires 20 nanoseconds to generate its result like sum and carry. It will take 20 nanoseconds of time duration for generating its output. Then for generating the complete result, how many time it takes? It takes total for 80 nanosecond here. Why? The second full adder starts its execution after getting the carry value from its previous stage, previous full adder. So this previous full adder, the first full adder takes 20 nanosecond. After that, the 20 nanosecond, it generates sum and carry output value. That carry output become the carry input of our second full adder. After getting this carry input from its previous full adder, second full adder start execution, start addition and generate the result sum and carry after next 20 nanosecond. And this carry output C2 form the carry input of our third full adder. And third full adder completes its addition after next 20 nanosecond. And it generate a result like S2 and carry output C3 here. So while after generating this carry output C3, the fourth full adder start addition and generate result after next 20 nanosecond. So as a total, it takes 20 into 4, 80 nanosecond for generating the complete result. This C4, S3, S2, S1, S0, that is the complete answer. So for getting that complete answer of this addition, it takes 80 nanoseconds time. This is due to this much time for generating that result is due to this carry propagation delay here. Okay, the situation get worse if we extend the number of stages for adding more number of bits. Means if the numbers which are given for adding contains more number of bits, then the situation gets worse. Means it takes more time for generating the complete result. Okay, so this is the case of parallel adder. So in order to reduce this carry propagation delay, now we can design another circuit, a modification in parallel adder circuit, that is carry lookahead circuit. So carry lookahead adder is a fast parallel adder as it reduces the propagation delay by more complex hardware. This is more complex structure and it is costlier. Okay, now we can start the design of this carry lookahead adder. So we have already discussed about the sum and carry output value of a full adder in our previous video. So these are the input combinations here. A and B are the two binary input to a full adder, and Cn is the carry input to that particular full adder, and these are the input combinations. So here these are the sum and carry out value. So this forms the truth table of our full adder circuit. So here we need to generate a modification over the carry circuit, right? That carry propagation actually causes delay, so we need to change, or we need certain modification over that carry circuit. Okay, so consider this carry output value only here, and these are the min terms corresponding to which the C out become 1 here in this truth table. So consider this min terms representation, that is A complement B C in, here A B complement C in, here A B C in complement A B C in. So consider this particular reduction we have already discussed in our full adder discussion video. So this is the final expression corresponding to our carry output in case of full adder. So this is the expression A XOR B and C in, or A and B. Once more, A XOR B and C in, or A and B. So now we can assign certain name for these terms, like this A XOR B can be called as A XOR B can be named as carry propagate, and this term after this or this term A and B can be named it as carry generate. This A XOR B is carry propagate, A and B is carry generator. So keep this term in your mind. The complete expression for our carry out is A XOR B and C in, or A and B. In this, the term A XOR B is named as carry propagate, A and B as carry generate. So consider this case. Okay, so here this is the expression, general expression corresponding to our C out from a particular level of full adder. Right? So Ci plus 1 is Ai XOR Bi and Ci, or Ai XOR Bi, in which this Ai XOR Bi is the carry propagator and Ai and Bi is the carry generator. This is the general expression for uh, Ci plus 1, carry output from ith stage. Ci plus 1 is equal to Ai XOR Bi and Ci, or Ai and Bi. Ai XOR Bi is the carry propagator, Pi. In short, we can represent as Pi. AI and BI is the carry generate term. In short, we can represent it as GI. Now consider uh, this three input combinations. Okay, here the carry output values are 0. For these particular three input combinations, the carry out is 0. So just analyze this particular term, this particular expression for Ci plus 1. When the Ci plus 1 become 1, here we have possibilities for the Ci plus 1 to be 1. One condition is if this term equal to 1. AI XOR BI and Ci equal to 1, then we don't want to consider this term. If this term is 1, then we can directly say that Ci plus 1 is 1. And other case, this term is 0, this is 0, but this is 1. This is actually OR operation. Right. So if this term is 0 and this term is 1, in that case also the Ci plus 1 become 1. Right. And if both this and this are 1, then also Ci plus 1 become 1. That means the carry out become 1. So these are the three cases due to which our carry output from a full adder become 1. If this term and this term, that means the two terms present in two sides of this OR operator, if both equal to 0, in that case, it indicate Ci plus 1 equal to 0. Means no carry is generated. Right. So consider these first three input combination. The first case is A equal to 0, B equal to 0, C in equal to 0. Right. So based on this input combination, consider our expression AI XOR BI. We have already learned this, the operation AI XOR BI. When this AI XOR BI become 1, this will become 1 if exactly one input equal to 1, then only output become 1. That means if this is 0 and this is 1, in this case output is 1. Otherwise, if AI is 1 but BI is 0, then this case also output become 1. If both are same, in that case output is 0. If both are AI and BI equal to 0, then also output becomes 0. If both AI and BI equal to 1, then also output is 0. If only one of the input is 1, then output become 1. Okay, so this is the condition of XOR gate, XOR operation. So based on our first input combination A equal to 0, B equal to 0, C in equal to 0, in this particular expression for our carry out, this is carry out Ci plus 1. So in this case, AI equal to 0 here, BI equal to 0 here, Ci equal to 0. All are 0. If AI equal to 0 and BI equal to 0, we can directly say that this carry generate term is 0. This is 0. And what about this AI XOR BI and Ci? This carry out is 0. If one term is 0 in case of AND operation, we can directly conclude this term is 0. This term is 0. So 0 or 0 is actually 0. So this is the case here. No carry is generated because of this particular input combination. Next case 0, 0, 1. If A and B again equal to A equal to 0, B equal to 0, C equal to 1. This is our new case. A and B equal to 0, then clear carry generator is 0. This term after this OR is 0. What about this part? AI 0, BI 0. If both input 0, XOR operation returns 0. One term is 0. Then 0 and Ci value is 1. That is 0 and 1 is 0 again. 0, 0. 0 or 0 is 0. So for this particular input combination, here again the carry out becomes 0. Means no carry generated. Another input combination 0, 1, 0. In this case 0, A0, B1, C0. Here A0, B0. So clear? A and B, that is 0 and 1 is 0. Carry generate term is 0. Here Ci is 0. So we can directly say that this Ai XOR Bi and 0 is 0. Again, before and after of this OR operator, that is 0. So carry out is again 0. No carry is generated. So these three combination indicate no carry generation. Next is our next three combination of inputs. These three. What is the property of these three input combination? Just consider. So in these three combination, here Cin is 1, Cout is 1. Cin is 0, Cout is 0. Cin is 1, Cout is 1. That means whatever value arrived in the Cin of a full adder, that is directly propagated to its Cout part. Right. Whatever value arrived as a Cin to a particular full adder, which is directly propagated to its Cout part in this three input combination case. So this is the case of carry propagation. So using this expression again, just analyze our prediction. Just analyze it. That is, in this particular case, input is A equal to 0. Here A equal to 0, B equal to 1, C equal to 1. Here A is 0, B is 1. Exactly one input is 1. In that case, we can conclude that XOR gate generate a value 1 and Cin is 1. So 1 and 1 is 1. So it is clear this particular part output is 1 for this particular input combination. And again A equal to 0, B equal to 1. So this generate part is 0. 0 and 1 is 0. So it is clear that here no carry is generated, but the previous carry is propagated due to this particular AI XOR BI term is due to this particular term AI XOR BI. AI XOR BI is 1 here. Due to that, this value Ci is propagated to next level. That is why this AI XOR BI is named as carry propagate. This is carry generate. Carry generate means this particular term generate carry without depending the previous carry value. But here it propagate the carry value whatever is present in the previous carry input. Whatever value is present as previous carry which is propagate to next level by this particular term AI XOR BI. So this is the propagate term of carry and this is the generate term of carry. Right. So consider our next case 1 0 0. 1 0 0 means A is 1, B is 0, A is 1, B is 0, C in is 0. So again one of this input A and B, here A is 1, B is 0. So A XOR B term become 1. But C in is 0. Right. So this term 1 and 0, this term now become 0. And here AI and BI. A is 1 but B is 0. So AI and BI become 0. 0 or 0 is 0 only. So whatever value present as a carry input to this particular full adder, which is directly propagate to its carry output. This is due to this AI XOR BI term. Here it is 1. Carry propagate term become 1. Due to this, it propagate whatever value present for this CI, it will propagate to next level. And consider the third case, that is A equal to 1, B equal to 0, C in equal to 1. A equal to 1, B equal to 0. Only one term equal to 1. So XOR term is 1. And C in is 1. So 1 and 1 is 1. This particular term become 1. And A is 1, B is 0. So generate term become 1 and 0 is 0 only. But this term is 1. So output become 1. That is, due to this term AI XOR BI equal to 1, it will propagate the carry value present here. That is, here carry is 1. That carry value is propagate to its carry output due to this propagate term equal to 1. Okay, now consider the remaining two input combination. In these two cases, it generate carry without considering previous carry. That is, without considering the C in input, these two input combination always generate the carry. That is, consider the combination A equal to, here A equal to 1, B equal to 1. A equal to 1, B equal to 1, C in equal to 0. A equal to 1, B equal to 1, C in equal to 0. So without considering this value, the carry generate term AI, 1 and 1 is 1 actually. So it generate a value 1. Okay, here A is 1, B is 1. Both input are 1. So the propagate term becomes 0. But here both A and B equal to 1, this carry generate term become 1. So it generate a carry without considering the C in. Okay, and for the next combination also, A equal to 1, B equal to 1, C in equal to 1. 1, 1, 1. In this also, both A and B equal to 1. So generate term generate a carry without considering what carry input value present here. It will always generate without considering the C in value. Both A and B equal to 1. So the propagate term equal to 0. So carry propagation will not take place here. Actually carry generation takes place here. So in these two input combination, it indicate that carry generation. The first three input indicate no carry generate. And second combination, these three inputs, it indicate carry propagate. And the last two input combination indicate carry generate. Okay. So now we can write expression for Cout and our sum using this carry propagate and carry generate. Once again, carry propagate is the term A XOR B and carry generate is A and B. Carry propagate can be represented using Pi, carry generate represented using Gi. So sum is, we know that we have already learned the full adder circuit. The sum is AI XOR BI XOR CI. So carry out, again carry output is AI XOR BI and CI or AI and BI. So consider this A XOR B. We can replace this A XOR B from this sum part as Pi. So we can rewrite this as Pi XOR CI. And here AI XOR BI can be replaced using Pi. AI and BI can be replaced using GI. So carry output can be rewrite as Carry output means Ci plus 1. Ci plus 1 is Pi, Ci or Gi. Once again, sum is Si equal to Pi XOR Ci. Carry output Ci plus 1 equal to Pi and Ci or Gi. So keep these terms in your mind. Si representation, Ci plus 1 representation in terms of carry propagate and carry generate. So consider a 2-bit parallel adder. The initial carry input is considered as 0 and the first full adder binary inputs are taken as A0, B0. And sum is represented as S0 here. Carry output of first full adder is represented as C1. And for the second full adder, inputs are A1, B1 and the carry from previous full adder, that is C1. And output is S1 sum, C2 carry output. So here we know that the carry output expression is AI XOR BI and CI or AI and BI. This can be rewrite like this. AI XOR BI is the propagate term. So PI and CI or AI and BI is the generate term. So GI. Right. Next is, now we can generate expression for the C1, C2 in terms of PI and GI here. How to write? The sum can be represented as S0. Can be represented as S0 is A0, B0, A0 XOR B0 XOR C0. And S1, A1 XOR B1 XOR C1. So in this, we can rewrite in terms of P0 and P1 as propagate 0 XOR 0. A0 XOR B0, rewrite it as P0. So P0 XOR C0, that is S0. Then S1, P1 XOR C1. So this is the expression for sum. Now consider carry. This is important. We need to generate a new expression or modification for this carry output expression or carry circuit in order to reduce propagation delay of carry. So this is the most important part. So carry 1. What is the expression for this carry 1? C1 is based on these A0, B0 and the carry input C0. Okay, so expression is Pi, Ci plus Gi. Pi means C1 is equal to P0 and C0 or G0. So C1 means P0, C0 or G0. So next C2, expression for C2. C2 is based on this particular general expression for carry out. C2 is P1, C1 or G1. P1, C1 or G1. Okay, and here our task is to convert C2 in terms of the C0. We need to avoid the C1 term from the expression of C2 and we need to replace this C1 using C0. If it possible, then we can reduce the carry propagation delay. How? Because if the C2 is represented using the C0, in that case, it is clear that this propagation delay get reduced. How? Because C0, A0, B0, A1, B1, all these input values are instantly available. But the C1 is not instantly available. This full adder circuit 2 need to wait until this full adder circuit 1 generate carry output value. And if it possible to convert the expression for the C1 in terms of C0, then we can reduce that propagation delay because this C0 is instantly available. So that is our aim. That is, we are going to derive an expression for our C2 in terms of 0 instead of the C1. So here C2 is represented initially like this: P1, C1 or G1. Now we have already this particular expression for C1. So replace this C1 using this. Replace this C1 with this expression. So C2 become P1 and C1 is replaced with P0 and C0 plus G0. So replace this C1 using this expression. Then distribute it. So finally C2 become P1 P0 C0 plus P1 G0 plus G1. So consider this term. So in this expression for C2, it is clear that here we have C0 only. Right? C1 is not present here. So all the terms present here are instantly available. We can instantly derive all these terms. The C2 depends only on this initial carry value C0 now. So all the terms present here are instantly available. So here it eliminates that carry propagation delay by converting all the carries based on this initial carry value, or representing all the intermediate carries based on our initial carry. Okay, consider some more generation like this. This is a 4-bit adder. Okay, and what are the instant values or instant inputs available? C1 is the initial carry. Here initial carry is represented C1 instead of C0. Here it is C1. And other instant values are A1, B1, A2, B2, A3, B3, A4, B4. All these binary inputs and C1 are instantly available, directly available when we start the addition. But this C2, it will generate only after the execution of full adder 1. And after generating the C2, it will form an input to this full adder 2, and using this instant value, the full adder 2 generate carry output C3 as well as our sum bit S2. So after generating the C3, full adder 3 start execution using this instant information B3 A3, and using the C3 it generates the third sum value S3 along with the next carry output C4. So our fourth full adder use this C4 carry along with this instant value A4 and B4. It generate its sum bit S4 and carry output C5. This will cause the carry propagation delay. In order to that, it will take more time to generate the full result. To avoid this, what we want to do, we need to derive expression for C2 in terms of C1, C3 in terms of C1 instead of the C2. We need to express C3 directly using C1 and C4 directly represent using the C1. Also the C5 directly represent using our initial instant carry input C1. If it possible, then it will completely eliminate that carry propagation time. For that, consider our propagation term AI XOR BI and generate term AI and BI. So based on this, sum can be represented PI XOR CI, carry output expression is GI, generate term, or PI and CI. Okay, so first generate the expression for our C2 based on our initial carry C1 and instant inputs A1, B1. Okay, so C2 is, this is the expression for our carry output. So C2 is represented as G1 plus P1 C1. Okay, and C3 can be represented. What is the direct expression for C3 based on C2? C3 is G2 plus P2 C2. Now the C2 can be rewrite using our above expression of C2. So C3 now become G2 plus P2 of G1 plus P1 C1. So while distributing, this become P2 G1 plus P2 P1 C1. Right. So from this expression it is clear C3 is expressed completely using our instant inputs. So it completely eliminates our carry propagation time. And what about the C4? C4, the expression, direct expression in terms of C3 is C4 equal to G3 plus P3 into C3. P3 and C3. G3 or P3 and C3. Now this C3 can be replaced using this particular derived expression. Okay, so this C4 become G3 plus P3 of G2 plus P2 G1 plus P2 P1 C1. So while distributing, this become G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 C1. So just analyze this in this C4 expression. Now it is completely represented using instant inputs. Here we use the first instant carry input C1 only. And all the other terms are based on our instant input. This A1, B1, A2, B2, A3, B3. So C4 is now represented completely using instant input. So it avoid or eliminate that carry propagation time. And similarly, what will be the expression for our C5? So C5 we can directly write using this C4 as G4 plus P4 C4. And we can rewrite this C4 using our derived expression thus term. So while rewriting this, C5 become G4 plus P4 G3 plus P4 P3 G2 plus P4 P3 P2 G1 plus P4 P3 P2 P1 C1. Again, here it use only one carry value, that is the initial instant carry input value, and all other terms G4, P4, G3, P4, G2, etc. All other terms are derived from our instant inputs like A1, B1, A2, B2, A3, B3, etc. So this is again, the expression for C5 is again expressed completely using our instant inputs. So it eliminates that carry propagation time. So this is how we can eliminate our carry propagation time while modifying our carry expression in our carry lookahead circuit. So this is the modification. Okay, so now we can draw that particular combinational circuit for getting that carry output of different level based on our previous expression. So we know that C2 is represented as G1 plus P1 C1. So we can represent C2 circuit as combinational circuit for our first stage carry output, that is C2 as G1 or P1 and C1. C1 is the instant initial carry input. This is the only one instant initial carry input, that is C1. So C1 P1 plus C1 and P1 plus G1. This is expression for C2, or this is the circuit part of G2, this portion. And next is expression for C3. We can convert this into this form by substituting the expansion for the C2. Now C3 is completely based on instant inputs and depends only on the instant input carry C1. So expression is G2 or P2G1 P2G1 or P2P1C1. Right. So next is C4. C4 can be represented as G3 plus P3 and C3. The C3 can be rewrite using this expression, so it become like this. So C4 is actually G3 plus P3G2 plus P3P2G1 plus means or P3P2P1C1. Okay, so next is consider one more carry output term, that is C5. C5 can be represented as G4 plus P4C4. That C4 can be rewrite using our derived expression, this one. So this become like this. So this is for you. Append one more circuit for this C5 using this expression. Try to draw that circuit or try to append that part of this combinational circuit here based on this expression. Okay, so this is a block diagram representation, logic diagram representation of our previous circuit. So first full ladder, here all these inputs are instantly available, C0, B0, A0. Based on that it generate the sum H0 and C1. So, and for the full ladder 2, it use a combinational circuit. That combinational circuit is based on the C0, B0, A0. That combinational circuit generate expression corresponding to the C1 based on propagate, carry propagate and carry generate term. That carry propagate and carry generate term is implemented using our previous instant input A0, B0 and C0. So here this particular combinational circuit generate our carry input to the second full ladder, use instant input A1, B1 and generate sum and carry output. And for our third full ladder circuit, here again it use some more complicated combinational circuit and use instant inputs like C0, B0, A0, A1, B1. C0, B0, A0, A1, B1. Using this, it generate an expression for our carry C2 and along with this carry 2, it use instant input A2 and B2 and generate sum and carry output. And our fourth full ladder, it use a complicated combinational circuit. That circuit actually depends on inputs, instant inputs like C0, A0, B0, A1, B1, A2, B2. Okay, using these instant input, it generate a value C3, carry input to this fourth full ladder. And using this instant input A3 and B3, it generate the sum and carry output value. Okay, so this is the logic diagram representation corresponding to our carry lookahead adder. And next is the same. Here we have this carry lookahead adder generator circuit, and this is the logic diagram in which the inputs are our instant inputs like initial carry input C1 and binary inputs A1, A2, A3, A4, B1, B2, B3, B4. Using these instant input, it generate propagate term and generate term of first full ladder, propagate and generate term of second full ladder, and so on. And using all these propagate, generate and initial carry input value, it generate different some bit of different full ladders along with carry output. Final carry output C5. Okay, so these are all about our carry lookahead generator circuit design, and also explained how it reduces the time of propagation of carry by generating expression for different intermediate carry directly using our instant carry input value. Okay, thank you.